Okay, so here is another example. We can use state machines to model the execution of threads. Here we just want to show you this example. In this diagram, we have two threads, and we use kind of state diagram to represent the states and also transitions between these states. And here, each of the states or transitions represent atomic instructions. If you choose one machine, one state, you will advance to the next state if guards are satisfied, like we talk about our finite state machine. In this particular example, there are 4 states for thread 1, another 4 states for thread 2. They share some of the states, and the transitions are a little bit different. The question here is, can thread 1 be in C1 at the same time thread 2 is in C2 state? Let's look at this example. So the threads are executing independently, but still they have one major attributes of these threads is that they share variables, they share the states. So if you have thread 1 in state C1 and thread 2 in state C2, what will happen is this thread 2, when it stays at C2, and when it evaluates C1, which is true because thread 1 is in C1. So C1, this guard satisfies. So you take this transition and to migrate to B2. And also, thread 1 will see at that moment C2 is true, so this guard satisfies. As a result, the thread 1 will transit to B1. Now, the same other thing happens because B1 and B2 are all true. So the thread 1 will take another transition, and similarly, thread 2 will take another transition. So it's kind of an interleaving transition that this will become a very dynamic process. So they will repeat this forever. So this particular case that it's not possible for thread 1 and 2 to stay at exact C1 and C2 states all the time. What we want to do in this example really is to show the dynamics between threads because they share variables, share states. So this has a significant impact on their operations. Next, we want to use a scenario from the aviation industry to explain a common software practice. Using modular avionics hardware, in these several physical systems, the software in the aircraft engine continuously run diagnosis and also publish the diagnosis data on the local network to all the other software systems and hardware systems on the local network. These diagnosis data may include the engine status, temperature, the oil tank, capacity, all these important metrics about the aircraft. And there are a lot of other systems will have to respond based on these data metrics. And also, on the other hand, there will be so-called observers or consumers of these data. For example, if you have a engine status rating number or engine speed number coming from the sensors, you want to display that number to different onboard display units so that the pilots can see, can observe, or some other control units will use the data to trigger any alerts, initiate any fault tolerance or safety measures. So there will be different consumers of this data to react on these data. So one side, there's a producer of data, and on the other side, there will be many consumer of the data. And that's what we call the observer process, which, for example, can update the cockpit display based on notifications from the engine about its status. So in practice, the software designers will use this so-called observer pattern that we'll talk about to map the data from one to many consumers or observers of the data. This is so-called the observer pattern that defines a one-to-many dependency between a subject and any number of observer objects, so that when the subject object changes states, all its observer objects are notified and updated automatically. Now, the way you understand the object here is really the software instances. And in our case, that's the thread. It's ideal application of these threads, where one thread is going to generate data, and maybe one or many other threads will be utilizing the data to perform a control or send to display units or trigger any safety measures. So this is a very typical thread programming problem. Okay, if you implement this observer pattern in C code, what we'll expect is we'll have something like this. We will declare a value that is used to record the status and also trigger notification of registered listeners. And we'll look at what is the listener functions for this case. Listeners is, you can think about it, it's a list of pointers to notification procedures or pointers to functions. And we define this notify procedure as a function that returns a void type pointer and takes one argument integer. And we also declare a struct called element, which will help us to build a list. And we will type def this kind of structure as element type, and it will declare a head and tail so that we can build this linked list. And then we have a procedure to add a listener to the list, and also we have a procedure to update the value so that the listeners, the functions can be called using this new value. And the exact procedure to call will notify, it's simply a print function. So this is the overall items or code that we should have in this C program. But when we look into this further, what we show here is the element structure. So the first is the notify procedure, this function pointer that we'll use to initialize the listeners. And this element structure is a node in the linked list. What we have here is as the element node, this notify procedure is the listener function. So we're going to initialize this as a function pointer. That's going to be some type of this type of function. And then we will use the next item on the structure to record the pointer to the next element. So if you're familiar with linked list, I'm sure you took data structure courses or used this linked list before, you know, this is how we build a linked list. We have the item in this node, and then we have a pointer to the next item. Sorry, pointer to the next node on this linked list. Okay. And for the add listener procedure, this is what we're going to do. We're going to take this function pointer as the argument. Basically, we want to add another node and then initialize the node so that it points to this listener function. In this procedure, we called add listener, we grow the linked list. We're going to check if the linked list has never been initialized. In that case, it has no nodes in this linked list, so the head pointer is a null. In this case, we're going to create the first node on this linked list. So we do malloc, create this node, and then we're going to initialize the listener function. So this is the pointer, and we're going to assign this listener pointer to this field in this node, in this element node. This listener is the one that passed in, and this listener is the field that's part of this node. And then the head next is a null pointer because this is the very first node that we created. So that's why there's nothing after this. So this is the only node. So the tail going to be also pointing to this head node. So you essentially create the first node on this linked list. If you already have a node on this linked list, then you're going to execute this path. In this case, we're going to grow at the tail. So we're going to create a new node by using malloc. And since tail is the last node, so I'm going to basically put the new node as its next. Before I do this, this tail next, it wasn't a null pointer. That's where you had here. And so I'm going to grow that. So I'm going to add a new created node to this tail. And I'm going to move the tail to the new node. So the new node is now the new tail. Then I'm going to put the listener, this function pointer that we pass in as the listener field of this newly created tail node. And then when we say this is the last one, so the tail next is now a null pointer. So this function, this procedure to add a listener to the list is a very typical way you grow the linked list and initialize the fields of this new node that's just created. Hope you guys are following. Any questions? Okay, let's see, there's one question. Okay, one question. Next procedure is the update. So update, think about you received the new sensor status from the engine. You want to broadcast it to all the nodes on the linked list. So every node has a function pointer, and you want to pass this new value to these functions so that they can be called. So this is what we do. This update procedure takes this new value as the input argument. And so this value here stores the new value. And we will then notify the listeners. And so we will go from the head. If there's no nodes created ever, this will be a null. So this while loop will be skipped. But if there's any node, we're going to start from the head. We're going to say, we'll call this listener. Now, this is how we use the function pointers if you have never done this before. Because element, this arrow listener, this is a function pointer. And when you use this heuristic, you are basically calling this function. Okay? You are, referring this function, and you add this parenthesis because the next thing you want to do is to pass in this value as the argument to this function, which is pointed by this listener. Okay, so this is how we do the function calls. If you just use listener pointer, this arrow listener, element arrow listener, this is the function pointer. If you want to call the function, you add this heuristic, and then you will then supply the input arguments. So we're going to call that, and then we're going to, after that function completes, we'll move on to the next node on the linked list. So we're going to move to the next one, and then check again until you finish going through all the nodes on this linked list. Okay, so this update function, even though it only has a few lines, it actually might take a long time, because this linked list, all the functions on this linked list will be called one by one. And this is how we call them. Okay, so what we showing here is another way to understand this update procedure. The code on the right side is what we saw just now. We have a update function. We use a new x as the argument that we pass in. And we use this while loop to go through every node on the linked list. So let's say we start from here. This is the first state because the default transitions are here. We will, when we have an argument, we will go to here. So we'll assign this argument to new x because somebody else called this function, and then the new x assigned to this other variable x, which actually we don't use here during these several lines. Then we move on to line 31. 31 is where we assign element to the first node on the linked list. That's always going to be true. It will finish that line, and then and the action is to assign the head pointer to this element. Now, starting from line 32, we're going to go through some loops. We will do the loop if element is not 0. If it is 0, then we're going to actually take this path. So we are done. We're going to be back to where we started. If this element is not 0, we're going to move on to the next line, which is line 33. What line 33 does is it will call these line listener function. It will use the new x as the input argument to call that function, and that's always going to be true because there's and that's the next line has to execute. Line 34 is line 34 is where we will have to move on to the next element, and that get back us to line 32. And eventually, by the way, so from line 32 to line 34 to line 32, the condition is that you return from listener, because this listener function depends on what it does. It may take a certain amount of time. So it transitioned from 32 to 34 to 32 only after this element listener finishes. Okay, so this is a interesting state machine that we can use to capture the execution of this procedure. Okay, so we went through the several important procedures, add listener, update, and we saw how we create the linked list by adding new nodes at the end of the list. And also we saw in the update, how do we use the linked list to access all the listener functions and call them. So we have a few questions here. Well, the central question here is, will this work in a multi-threaded context? So everything what you saw just now, looks reasonable. If you remember the code that we used to create the linked list, seems it properly considers different cases. When the head is null, so there's no nodes, and what do we do? If there is already nodes, then we'll add new ones at the end. When we do the update, we will go through the linked list, call the functions one by one until we finish iterating the nodes in the linked list. So everything seems perfect. But then we have potentially serious issues when we do this in a multi-threaded environment. And that's what we're going to discuss in the next 10-20 minutes. This is the procedure that we saw earlier. Add a listener to the list. Okay. So if the head is 0, we're going to create a new one, and we have the head pointing to the new node and also tail pointing to new node. If there's already nodes, we're going to create a new one and assign it to the end of the tail. And then we're going to move the tail and initialize the function pointers, and then put the next to be 0 and so on. Now imagine what we have here, the same code, but now being executed by 2 threads. And it's typically, it's perfectly possible, because this is a program that you write for all these functions. Most of the functions, you can have a way to wrap them and then execute in a thread. When you have 2 threads, let's say, thread A and B are executing, and thread A gets to this point, it does allocation, okay? It tries to add a new node at the tail of this linked list. So it finishes this malloc. So the tail next pointing to the newly allocated node. Now, unfortunately, at this point, the thread scheduler decide to suspend this current thread. So at this point, it's not executing the next line. Thread B is now being executed. The thread B also get to this point, it'll execute this allocation and it will assign this newly allocated memory to the tail next. But guess what? They are accessing the same variable. This tail is the same, but now the node which was just allocated by thread A will be lost because now the tail next pointing to the very last new node that was just created. And subsequently, this tail next will be overwritten. So the original the node which was allocated by thread A will be just there's no way you can recover it. And of course, you have serious issues with memory allocation, and also the tail pointers will be now pointing to the wrong location. I hope I can have a better picture to visualize this, but I hope you can follow what I was just described. It's because these tail and this also head variables are shared by these multiple threads. So if at any point these sequences are interrupted or interleaved between these different threads, these pointers will be incorrectly assigned or initialized. The value will be not properly setting up these continuous linked list. So that's the danger we are facing when you have multiple threads executing concurrently, and when they access shared variables, which they can because all these variables are shared, and then they will create serious problems. This is called race condition, which essentially is the concurrent code trying to access the same resource, i.e. the shared variables. In order to address this problem, we need to use so-called mutually exclusive clocks or mutex, so that whenever we try to access the shared variables, we should have a way to protect them from this unintended concurrent accesses to make sure the operation is still valid or producing valid results. Here's one possible solution. We use so-called pthread mutex lock. Mutex lock stands for mutually exclusive locks. We will have to declare this lock at the very beginning. So it's a pthread mutex lock. It's called a lock. This variable name is lock. And we have, when we use the linked list, for example, add listener, we have the code that we saw earlier to grow the linked list. So we'll have to protect that so that only one of the threads will be able to access these shared variable. And once we finish, we'll have to release the lock. So that's why you see this lock and unlock pair appear in this add listener function. And correspondingly, we also need to have these mutex lock applied in the update function, because in the update function, you also access the linked list. So when you try to access this linked list, chances are, if you don't do this, the add listener procedure will try to add a new node into this linked list. But during that process, if you interrupt at different places, it may happen that the tail of the pointer points to an unintended location. And if you don't have this lock, then this while loop will possibly access a node which has its listeners not initialized yet. Because if I go back, this is where we initialize the listener. So if for some reason this thread is interrupted or suspended at this point before the listener pointer is initialized, then this update function, when it goes through the linked list, it may happen to see a uninitialized listener pointer. And if you use that to make this function call, then that will cause segmentation error. Okay. Now, we seem to have a solution, but unintentionally, we have a potential deadlock risk. Deadlock risk is where you are trying to, you have more than one lock, and one of the running instances or thread holds a lock, and it tries to acquire another one. And on the other hand, you have another thread which already acquires the second lock, but trying to acquire the first lock. In this case, the threads will both hold one lock, but still trying to acquire the other lock. And that's where the deadlock happens. In this code, we didn't show the second lock, but it may happen, for example, this listener function. In this listener function, because it uses a lot of the shared variables, you may have to use another lock to protect another shared variable. In that case, you may have a second lock or even more than two locks, and that will, that will be the potential risk to have deadlock situations. There was some solutions, but none of those turned out to be universally, correct or guarantee there's no deadlocks. Even this project from Berkeley, they had a lot of code review of this Ptolemy projects. They had code review, found a situation the thread was not safe. They fixed this thread, but later on, the deadlock showed up in a test suite. So deadlocks are really a very hard problem to solve. It's not obvious, and not all the test cases can reveal the problem. It requires a lot of verification using tools to analyze the code. Even that, sometimes is not guaranteed that deadlocks can be discovered. One possible fix of that is to use copies of shared variables. In this case, we copied the list of listeners before we access them. So this will reduce the possibilities of deadlock and also avoid race conditions. So here between these lock and unlock, we will make a copy of the list of listeners. And so when we get out of here, we will use the new copy to go through the linked list. So in this way, they will not be able, they will reduce the condition, the risk of the deadlocks. But there's also issues with this design, in a sense that if the multiple threads call the update function, the update will occur in some order, but still there's no guarantee that the listeners will be notified in the same order. So if you have a new value, because the listeners will be, this part of the execution will be non-deterministic. So the listeners may see the old value or not the most recent value. So if you use that to, let's say, update the display in the cockpit display in aircraft, you may see the new value and the old value mixed up in certain cases. So listeners may not be able to get the final value of the shared variable.